severe icing is an emergency. Just like an emergency descent. You don't have to wait for clearance. Just get down right away. Hello aviators, how are you today? My name is Magnar. I'm an airline captain and instructor on ATR aircraft. Commercial air transportation is the safest way you can travel over long distances. Every day are millions of people blasting through the air at 850 km per hour, more or less, while they are sipping a glass of wine and enjoying their favorite movie. Okay, they're low-cost carriers, but you got the point. Traveling in an airliner is incredibly safe, but it has not always been that way. Being an airline passenger 100 years ago was an adventure, a rather risky one. The safety level we take for granted today is the result of bright ideas, dedication, and accidents. Yes, you hear me right. Accidents have made the aviation industry safer because they have given us better understanding of the risks associated with flight. And as a result, we have better rules, better machines, and better training. Here are some examples. Before two accidents in 1954 with the first jetliner, the de Havilland Comet, very little was known about airframe metal fatigue caused by the expansion and retraction of pressurized cabins. Before the accident with Delta Airlines Flight 191 in 1985, little was known about the microburst, a type of wind shear with an incredibly strong downdraft. And before the accident with American Eagle Flight 4184 in 1994, very little was known about supercooled liquid drops, SLD. This accident changed that. It also made ATR a scapegoat. Even today, 29 years after the accident, do many people believe that ATR is unsafe in winter conditions. But the world is not black and white. And what I'm going to tell you might surprise you. But first, let's talk about aircraft icing, because it has a lot to do with this accident. Water droplets form in the atmosphere when moist air is cooled down. The droplets are very small and will form clouds or fog if they are over the ground. The droplets will collide with each other and grow, and if the process is repeated enough times, the droplets can grow into drizzle and raindrops. While the temperature is below freezing, it doesn't mean the droplets will have to freeze. They can remain in a liquid form at temperatures well below freezing, and will only freeze when they hit an object, for example a dust particle or an aircraft. Ice accumulation on an aircraft will add weight and drag, and it will reduce the thrust, and since it alters the wing profile, it reduces the lift, and the wing will stall at a lower angle of attack. Aircraft certified for operating in icing conditions are therefore equipped with ice protection systems. They protect the most important areas like air data probes, wings, tail, air intakes, and propellers. And this video here explains how it works on ATR aircraft. Icing conditions are classified into four groups: trace, light, moderate, and severe. Trace ice is when the rate of accumulation of ice is slightly greater than the rate of loss of ice due to sublimation. Light icing is when the rate of ice accumulation may create a problem if the accumulation continues for more than 1 hour. Moderate icing is when the rate of accumulation is such that even short encounters become potentially hazardous. Severe icing is when the rate of accumulation is such that de-icing and anti-icing equipment fails to reduce or control the hazard, and immediate heading or altitude change is required. You might be surprised to hear that moderate icing is a safety hazard. Well, here's a report from Aviation Herald about an incident that happened just a couple of weeks ago. An Air Canada Bombardier C-Series CS300, which is now known as the Airbus 220, registration Charlie Golf Whiskey Uniform Tango, performing flight AC-1074 from Denver, Colorado, United States, to Montreal, Quebec, Canada, was on final approach to Montreal's runway 24 right. An Air Canada Rouge Airbus A319-100, registration Charlie Golf Bravo Hotel Yankee, performing flight RV 1597 from Halifax, Nova Scotia, to Montreal, Quebec, was on final approach to runway 24 right behind Charlie Golf Whiskey Uniform Tango. The Canadian NTSB reported that there was moderate icing between 2,200 and 8,000 feet. The A319 encountered a significant increase in ice accumulation while descending through 3,000 feet. AC-1074 slowed down, prompting the controller to request RV-1597 to slow down too. However, the required separation of 3 nautical miles between the two aircraft was lost and reduced to about 2.1 nautical mile. The controller instructed RV-1597 to go around. The crew, however, requested to continue the approach for safety reasons due to the icing conditions. The controller permitted RV-1597 to continue the approach and requested the crew to advise when it had AC-1074 in sight. Both aircraft were in IMC at the time, but RV-1597 had AC-1074 on their TCAS display. Finally, the crew reported to have AC-1074 in sight and was cleared for a visual approach. Both aircraft landed safely. This crew understood the potential hazard of going around and being exposed to more icing. Not even powerful airliners with powerful ice protection systems are immune to the elements. Good job! Sadly, the crew of American Eagle Flight 4184 faced even worse conditions, and they did not have the knowledge we have today. American Eagle Flight 4184 departed Indianapolis at 2:55 p.m. Central Standard Time on October 31, 1994, en route to Chicago's O'Hare International Airport. There were 64 passengers and 4 crew members on board the ATF-72 turboprop. Air traffic controllers directed the pilots into holding pattern due to delays in Chicago. While circling, the aircraft encountered severe icing conditions, which led to a loss of control. Flight 4184 entered a high-speed dive and crashed in the second field behind this monument at 3:57:56 p.m. Central Standard Time. There were no survivors. The National Transportation Safety Board investigation determined that ice buildup on the wings led to a loss of control of the aircraft. The sequences that led up to the accident are well documented by Disaster Breakdown. There are many creators making videos about aviation, but few of them put so much effort into explaining why and how as Disaster Breakdown. Every detail is correct. The channel is hereby recommended. So, instead of repeating how the accident happened, I will in this video focus on what happened after the accident, because that is a story you may have never heard about. If you want to brush up your knowledge about the accident, please watch the video from Disaster Breakdown. You will find a link in the description below. To get everything into context, I will have to explain a few things first. If you know about Supercooled drops, Uncommanded aileron deflection, and Vortex generators, you can proceed to this chapter. You will find the link below. As I said, supercooled droplets will freeze to ice when they hit an object, for example the wing of an aircraft. Cloud droplets are very small and will freeze instantly when they hit the leading edge of the wing. This ice is white and called rime ice. Turboprop aircraft like the ATR are equipped with the pneumatic de-icing boots. They are made of bladders that alternately inflates and deflates, thus breaking away the ice. In this picture, the ice accumulation is very small, so the ice will barely break away. When the drops are 50 microns or larger in diameter, that is 0.05 mm, we have freezing drizzle. And when the drops are 500 microns or larger, we have freezing rain. They are called supercooled large drops, SLD. The larger the drops, the longer time it will take for them to freeze. So when they hit a wing, the drops will flow along the surface of the wing while freezing. Until 2015, no new aircraft types in the transport category were certified to fly in SLD, which is freezing drizzle and freezing rain. The crew of Air Canada Rouge Flight 1597 understood this and decided to land even when this resulted in a reduced separation. because it was more safe. The ailerons are used to control the roll. When we move the control wheel to the right, the aileron on the right side moves up, reducing the lift on that side, while the left aileron moves up, increasing the lift on that side. This creates a rolling moment, and vice versa. Turboprop aircraft like ATR, Dash 8, Fokker 50, Saab 340 have manually operated ailerons. While this makes the design lighter and less complex than hydraulically boosted ailerons, it makes the aircraft prone to what we call uncommanded aileron deflection. Let me explain. In normal flight, the ailerons are balancing each other out, which means the hinge moment on one aileron is compensated by the hinge moment of the opposite aileron. The net force on the pilot's control column is therefore very low. But in case of an uneven lift distribution over the wings, for example because of a turbulent airflow, the hinge moment on one side will change significantly, causing the ailerons to deflect by themselves, resulting in an uncommanded roll. And this aerodynamic force can overpower the pilot. A vortex generator is a small vane attached to the surface of a wing, stabilizer, or control surfaces such as flaps, elevators, ailerons, and the rudder. The vortex generator creates a vortex which delays local flow separation and aerodynamic stall. This makes the wings, stabilizers, and control surfaces more effective. This is the wing of a Douglas A4 Skyhawk. The vortex generators allow the aircraft to fly with a higher angle of attack, which means it can fly at less speed and or carry more weight. Very useful for aircraft carrier operations. The ATR wing is a non-laminar flow design. NACA 43-018 profile is used at the wing root and NACA 43-013 at the wingtip. The wing provides high lift and low drag, but it has a relatively abrupt stall behavior, which is indicated by the sharp drop in the lift curve. The ATR 42 was certified in 1985. At that time, the wings did not have vortex generators. When ATR later developed the ATR 72, it was discovered that uncommanded aileron deflection could happen at an angle of attack that ATR deemed to be too low. The solution was to add vortex generators on the upper wing surface, in front of the ailerons. This delayed the uncommanded aileron deflection to 25 degrees angle of attack, which is well beyond the stall. Earlier, there had been some incidents with ATR 42 experiencing uncommanded aileron deflection in icing conditions. As a response to this, ATR added vortex generators to the ATR 42, which was approved by the French aviation authorities, DGAC, in 1990 and by the FAA in 1992. But when ATR wanted to change the AFM, Airplane Flight Manual, and FCOM, Flight Crew Operating Manual, describing the purpose of the vortex generators, some authorities said no, it's not necessary. The French DGAC stated they did not require the changes because they addressed a condition outside the certification envelope. Likewise, the FAA considered that the vortex generators would remove the source of the abnormal aileron behavior. However, the Canadian and German CAAs both implemented the changes. While some aircraft have a reputation of being able to carry a ton of ice, the ATR is more sensitive. The wing doesn't like ice contamination that much, but this is nothing new. Enter the Quickie. It was designed by the Burt Rutan and friends. The Quickie has a low horsepower but high cruise speed, and it became popular among home builders. A friend of me had a single-seat version of the Quickie, and he told me that the rain caused water drops to stick to the canard wing, and this made it impossible to take off. The ATR wing is not affected by rain, and the de-icing boots are very effective because they are lined chordwise. ATR is also equipped with an automatic ice detection system, alerting the pilots when ice forms on the airframe. The aircraft also has an ice evidence probe outside the captain's side window, showing the extent of ice on unprotected surfaces. I started my ATR training in November 1999 at ATR Training Center in Toulouse, France. This was 5 years after the accident with Flight 4184, and there was a lot of focus on icing procedures. And this made sense for me because I am from Norway, where icing is almost a daily occurrence. My previous experience was on Jetstream 31, which is not the best performer in icing conditions. During an ATR typewriting course, you learn how the ice protection systems work, and I have made a video just about that, and you find a link in the description below. Next, you will learn when and how to use the ice protection systems. When ice forms on the aircraft, it will increase the drag, reduce the lift, and the stall angle will decrease. Therefore, minimum safe speeds are higher in icing conditions. This table shows minimum operating speeds for an ATR 72 at 20 tons. That was the weight of our American Eagle 4184. Minimum speed with flaps retracted is 133 knots in normal atmospheric conditions and is marked with a white bug on the airspeed indicator. Minimum speed with flaps retracted in icing conditions is 158 knots and marked with a red bug in icing with an analog airspeed indicator and an amber bug in aircraft with a glass cockpit. After the introduction of the 600, it is now called the icing bug. When we activate the anti-icing systems, the stall protection system changes mode from normal conditions to icing conditions. In normal conditions, the stall alert system in an ATR 72-210 will trigger the stick shaker at 11.6 degrees angle of attack. At 13.5 degrees angle of attack, the stick pusher is activated. And this is how we test the stick shaker and pusher. Therefore, when the stick shaker is activated, the aircraft is still under control. In icing conditions, the stick shaker is activated at 8 degrees angle of attack and the stick pusher at 10.6 degrees angle of attack. Once we were familiar with the ice protection systems and the procedures, we proceeded to severe icing. During the training, we learned how to recognize severe icing and how to escape it. And here are some clues to identify severe icing. There will be splashing water on the windscreen, you have loss of performance, there is an excessive accumulation of ice on the ice evidence probe and the side windows. This happened to me once, not in Norway, but in tropical Thailand. This was a flight from Bangkok to Yangon in Myanmar. When we were on the border between the countries, we saw a large cloud formation ahead of us. We could not climb above it, and it was too wide to circumnavigate. The weather radar showed green over a large area, so we didn't expect much ice. Before we entered the cloud, the anti-icing systems were switched on. After a while, the ice detector was triggered, and we switched on the de-icing systems. All systems worked normally. Shortly after, water started to splash on the windscreen. The side windows iced up in seconds. This picture was taken a few minutes later, after we had escaped those conditions. We started to lose airspeed. It was time to act. Set MCT power, start descent. Autopilot off. When it comes to icing, speed is king. We descended to warmer air and the ice started to melt away. While we did that, we called ATC and informed them what was going on. Severe icing is an emergency and you do not have to wait for clearance to descend. Get down now. The reason we disconnected autopilot is that the pilot can feel the aircraft and flying manually. If the aircraft starts to behave erratic in roll, you must apply the stall recovery procedure. Push the nose down, add power, and if the flaps is retracted, set flap 15. In my case, we did not experience control problems because we maintained a high speed. As explained by Disaster Breakdown, American Eagle Flight 4184, operated by Simmons Airlines, crashed because an ice ridge formed after the de-icing boots on the top of the wing. This disturbed the airflow over the ailerons when the angle of attack increased and resulted in an uncommanded aileron deflection, also known as aileron hinge moment reversal. Initially, the autopilot compensated for this by applying more aileron, but as the force on the aileron increased, the autopilot reached the limit and disconnected. This caused the ailerons to snap to maximum deflection, which took the pilots by surprise, and they lost control. Why did the ice ridge form behind the de-icing boots? There were two factors. One, large supercooled drops freeze slowly when they hit the aircraft. Tiny cloud droplets will freeze instantly, but large drops will flow along the surface while they are freezing. 2. The crew used flap 15 and holding. When you extend the flaps, the aircraft will pitch up. This is compensated by the autopilot by lowering the nose of the aircraft. Because of this and a relatively high speed, the aircraft was flying with a very low nose attitude. This caused ice to form behind the de-icing boots. This ice ridge was not even, but formed and broke off with irregular intervals. This led to a turbulent airflow over the wing, a recipe for uncommanded aileron deflection. When the crew then retracted the flaps, the aircraft started to pitch down, and this was compensated by lifting the nose, increasing the angle of attack. When the angle of attack exceeded 5 degrees, control was lost. Therefore, the stall warning system was not triggered. Just to be clear, the aircraft did not stall. Control was lost when the ailerons were forced to full deflection. When the pilot reduced the back pressure on the control column, the angle of attack decreased and he regained control of the aircraft. But this caused the aircraft to pitch down. So the pilot pulled up again, and this caused the angle of attack to increase and control was now lost. The aerodynamic forces acting on the ailerons were stronger than the pilots. This accident highlighted a problem. While a transport category airplane is certified for flight in icing conditions, it is the pilot's responsibility to ensure that the airplane is operated within the certified icing envelope. At the time ATR 42 and 72 were certified, the requirement was that the aircraft can operate safely in icing conditions where the water droplet size does not exceed 50 microns. But how can a pilot distinguish between water droplets with a size of 50 microns from larger drops? The National Transportation Safety Board, NTSB, concluded that the aircraft was certified in accordance with the regulations in JAR Part 25, that's for Europe, and FAR 25 for the US. But the certification standards for transport category aircraft did not address icing caused by supercooled large drops, SLD. The NTSB did also conclude that the authorities, the French DGAC and the US FAA, had failed to take the necessary corrective action to ensure continued airworthiness of ATR aircraft in icing conditions. The reason was that there had been 5 incidents where ATR 42s had experienced uncommanded roll in freezing precipitation. The last reported incident was in January 1994. In all cases, the crew regained control of the aircraft. The NTSB blamed the authorities for inadequate oversight of the aircraft type, and they blamed ATR for inadequate response to those incidents. When studying data from the before-mentioned 5 incidents with ATR 42, ATR noted that the propellers had been operated at 77% RPM. This increased ice accumulation on the propeller blades, which increased the drag and reduced the thrust. ATR procedure is, when flying in icing conditions, the RPM must be 86% or higher. And do you remember the Vortex generators ATR introduced to the ATR 42 in 1990? It took FAA another 2 years to give the approval in the United States. and they declined ATR's offer to provide information about the Vortex generators in the manuals. But there had also been an accident. In 1987, an ATR 42-300 departed Milan Linate Airport in Italy for a flight to Cologne-Bonn Airport in Germany. The SID, standard instrument departure, required the aircraft to climb with a steep gradient to flight level 140, or 14,000 feet. Milan is just south of the Alps, a mountain range with tops up to 15,780 feet. The aircraft climbed on autopilot with IAS mode, indicated airspeed, set to 133 knots. This was whitebug plus 10 knots, the speed for the best rate of climb in normal atmospheric conditions, with a weight of 15 tons. The aircraft entered icing conditions, but the crew did not increase the speed to minimum speed in icing conditions, icing bug, which is 146 knots at this weight. When passing flight level 147, the aircraft rolled right and left 2 times before it entered a dive. The accident report states that the pitch trim was moved forward, nose down, 3 times, preventing recovery. The aircraft crashed into a mountain and all 37 on board died. It was reported heavy rainstorms in the area, indicating severe icing. In Italy, airline accidents were investigated by the Carabinieri, and they concluded that the accident happened because of a design error. The designer of the aircraft, together with 3 senior executives of the airline company, were convicted for manslaughter. ATR concluded that the accident happened because of pilot error. The aircraft had been flown with a speed 30 knots below icing bug, and the use of the trim had prevented recovery. In 1981, the NTSB published a report entitled Aircraft Icing Avoidance and Protection. The primary issues included icing standards for aircraft certification, weather forecasting, and aircraft performance in icing conditions. The NTSB recommended to the FAA to revise 14 CFR Part 25, Appendix C, icing certification envelopes to include freezing rain. The initial response from the FAA was, quote, "We believe the present icing certification philosophy and criteria are basically sound," end quote. The NTSB considered this response to be unacceptable and continued to send letters to the FAA. This correspondence continued for more than a decade. In September 1994, 2 months before the accident, the FAA wrote, quote, "The FAA has concluded that the icing criteria published in 14 CFR Part 25 is adequate," end quote. You can download the accident report, there is a link below here, and read the full story in section 118. However, after the accident, things started to change. In May 1996, FAA sponsored an international conference on aircraft in-flight icing. At the conference, recommendations were made regarding the need for improvements intended to increase the level of safety of aircraft operations in icing conditions. In November 1997, an Aviation Rulemaking Advisory Committee, ARAC, was tasked to define the icing environment that includes SLD and devise requirements to assess the ability of aircraft to safely operate, either for the period of time required to exit the conditions or to operate without restriction in SLD. In November 2005, the AARC forwarded to the FAA proposals for new rules for the flight in SLD. And finally, in January 2015, FAA and EASA issued amendments to 14 CFR 25.1420 and CS-25.1420 respectively. Yes, it took 34 years to change the rules. Before the accident with Flight 4184, the ATR AFM stated the following: Operation in freezing rain must be avoided. Most pilots do not use the AFM, they use the FCOM, Flight Crew Operating Manual, because it's more detailed. However, at the time of the accident, the FCOM was not crystal clear about flight in freezing rain. In 1992, ATR issued a brochure entitled All-Weather Operations. It contained information regarding operation of the ATR airplanes in icing conditions. In this brochure, ATR stated, quote, "Out of freezing rain is not part of certification cases. It must be taken into account for operations in icing conditions. And flight in freezing rain should be avoided where practical." End quote. The brochure also gave the following warning. Ice accretion due to freezing rain may result in asymmetrical wing lift and associated increased aileron forces necessary to maintain coordinated flight before aerodynamic stall. ATR distributed the brochure to all ATR operators. ATR also attempted to send a copy directly to all ATR pilots. But Simmons Airlines did not distribute the brochure to its pilots. The reason was that they considered some of the information to be contrary to the Federal Aviation regulations. However, some of the information from the brochure was later included in the company's manuals. The operations manual stated that the dispatch of airplanes shall be conducted to avoid flight into freezing rain conditions, but neither the flight manual part 1 nor the AOM stated that flight in freezing rain should or must be avoided, as stated in the ATR AFM. On the 6th of January 1989, Simmons Airlines issued a memorandum to the pilots entitled Flight into Icing Conditions. It stated, quote, "Our aircraft are not to be operated in known freezing rain or severe ice." End quote. On the 15th of November 1991, the company distributed a memorandum to its pilots entitled Flight Operations in Freezing Rain. The memo stated, quote, "It is emphasized that aircraft ice protection systems are designed to cope with the supercooled cloud environment, not freezing rain. Large droplets, 1,300 microns, large rain droplets, of freezing rain impact much larger areas of the aircraft components and will in time exceed the capability of most ice protection equipment. Therefore, flight in freezing rain should be avoided where practical. Simmons aircraft are certified for flight into freezing drizzle and light freezing rain." No, at that time, no transport category aircraft was certified to fly in freezing precipitation caused by SLD. Just like the term microburst, the term SLD was just not invented yet. Freezing drizzle drops are between 50 to 500 microns in size. Freezing raindrops are larger. And even if the aircraft had been certified to fly in freezing drizzle, how can a pilot know the difference between freezing drizzle and freezing rain when in flight? After accident, ATR implemented changes to the aircraft and the procedures. At Edwards Air Force Base, the US Air Force had a Boeing NKC-135A Stratotanker. It was modified to carry out icing tests. It was equipped with a boom with a spray nozzle that could produce a cloud of supercooled water drops of various sizes. In December 1994, few weeks after the accident, an ATR-72 was flown behind the tanker, recreating the conditions experienced by Flight 4184. Following those tests, ATR modified the upper part of the de-icing boots outside of the engines to extend further aft, from 7% to 12.5% MAC. An aircraft with the new de-icing boots was tested in March 1995. The test demonstrated that no ice formed after the new de-icing boots. All US registered ATR 42 and 72 aircraft were modified with the new boots before June 1995. When ATR introduced the 42-500 and 72-500, they introduced a new computer, the APM. The APM, Aircraft Performance Monitoring System, compares actual aircraft performance with a theoretical model. It will alert the pilots when ice accumulation causes excessive drag. If the cruise speed drops 10 knots below normal cruise speed, the message "cruise speed low" is triggered. If during cruise the drag increases with 22% or more, and the cruise speed is 15 or 20 knots below theoretical cruise speed, the message "degraded performance" is triggered. Or if during climb or descent the drag is 28% or more, and the speed is more than icing berg plus 10, degraded performance is triggered. This is an indication of severe icing, therefore action is required. If the speed drops below icing berg plus 10 knots, the message "increased speed" is triggered. And this is your last warning. Get your speed up or you will face the consequences. Almost every incident and accident related to icing happens because the pilots let the speed drop below the minimum operational speed while ignoring those signals. The accident report stated that, at the time of the accident, it was common for the pilots in the company to fly in holding with the flaps extended. After the accident, ATR emphasized that flying in holding with the flaps extended is prohibited, unless you're single engine in icing conditions. ATR also revised the procedure for flight in icing conditions. When I learned to fly the ATR 42 in 1999, the procedure was minimum speed in icing conditions, icing bug, minimum speed with ice accumulation, icing bug, minimum speed in severe icing, icing berg plus 10. The simulators were upgraded to replicate severe icing. But there will be 2 more accidents with ATR 72 in severe icing. Trans-Asia Flight 791 in 2002 and Aero Caribbean Flight 883 in 2010. In both accidents, the pilots let the speed bleed off below icing berg while they waited for clearance from ATC to descent. By doing so, they lost control. Severe icing is an emergency, just like an emergency descent. You don't have to wait for clearance. Just get down right away. After the second accident, ATR changed the procedures to the following: minimum speed in icing conditions, icing berg, minimum speed with ice accumulation, icing berg plus 10 knots, minimum speed in severe icing, icing berg plus 30 knots. When it comes to icing, there are 3 things to remember: airspeed, airspeed, and airspeed. Despite the introduction of the APM and the procedure have become more and more conservative, there have still been incidents where ATR pilots have let the speed decay below the minimum operational speeds. I have made a video about just that. It's here. You will find a link in the description below. So you might start to wonder, is this a problem with the aircraft or the pilots or both? What about other turboprop aircraft like Dash 8, Embraer 1220 Brasilia, Saab 340? Are they immune to ice? No. What all turboprop passenger aircraft in this size have in common are pneumatic de-icing boots and manually operated ailerons. While uncommanded aileron reverses is a rare occurrence, there have been icing-related accidents and incidents with those aircraft types. Here are some of them. Embraer 120 in 1997, loss of control due to uncommanded roll during approach, fatal crash. Embraer 120 in 2001, loss of control during cruise resulted in loss of 8,000 feet and structural damage to horizontal stabilizer and elevator. Saab 340 in 2006, stalled and lost 5,000 feet. Dash 8-100 in 2012, stalled and lost 5,200 feet. Saab 340 in 2014, stalled during cruise. Therefore, some manufacturers let the aircraft undergo the same icing tests as the ATR 72 in 1995. All of them demonstrated that they could be flown safely in those conditions. So, if they have demonstrated they are safe in icing conditions, what is the problem then? In 2005, Flight Safety Foundation released an article understanding the stall recovery procedures for turboprop airplanes in icing conditions. The author interviewed managers from 3 aircraft manufacturers. While it is not mandatory to include stall recovery procedures in the manuals, ATR has published procedures for stall recovery with and without ice accretion. The manuals for Beechcraft King Air include only a recommended procedure for recovery from non-ice related single engine stall. Bombardier stated they do not include the stall recovery procedure in the manuals for the Dash 8 because it is not required to be there. At that time, in the US, there was a requirement for pilots during shake rise to demonstrate a recovery from a beginning stall without losing altitude. The mantra was to add power and accelerate out of the situation. That doesn't work when an aircraft is dragged down by ice. In 2009, a Dash 8 Q400 crashed during approach. That was Colgan Air Flight 3407. Shortly after extension of flaps and landing gear, the stick shaker activated. The captain reacted by pulling the nose up and the stick pusher activated. But the captain overrode the pressure by pulling back on the control column, causing the aircraft to stall. At the same time did the first officer retract the flaps. The NTSB determined that the current stall training was not good enough. As a result, the aviation industry has revised the stall recovery procedure to be as following: push the nose down and increase power as required. Some aircraft types like the ATR requires the flaps to be extended if it was in a retracted position before. Each action alone will break the stall, but lowering the nose is the most effective, as the angle of attack is instantly reduced. Accidents do not happen because of a single cause, and American Eagle 4184 was no exemption. I am sure you are familiar with the Swiss cheese model. In this case, we can list up the following threats and errors that led up to the accident. 1. The wing is sensitive to ice. 2. The information in the aircraft manuals, AFM and FCOM, was not consistent. 3. Passive aviation authorities. 4. A common belief that transport category aircraft are certified to operate in freezing drizzle and light freezing rain. 5. Use of flaps in holding. 6. Training might be a factor, especially when it comes to detecting severe icing. When looking at ATR today, we see that a lot has been done to address those threats. There have been improvements to equipment, procedures, and training. And that's all I have to say for this time. This video is already very long, but it could have been much longer. The accident report alone has more than 300 pages. But I think I have the essentials covered. What do you think? Could this accident have been prevented? Or can it happen again tomorrow? Let us know in the comment section below. Thank you for watching, have a wonderful day and happy landing.